Hi, my name is Ruslan Srinivasan, and this is my AE1601 glider report. So, starting out, the glider's name is Aero Zenith, and a short overview of the project is that we had to design, build, and flight test a small glider over the remainder of the semester. We also had to use materials found around the home for construction, in addition to balsa wood. So, for the approach, I applied existing knowledge and conducted necessary research, and iterated a practical and feasible design through a creative process. The nature of the project was open-ended design problem with no strict solutions. It encouraged creativity and innovative thinking. The final outcome was that we had to conduct a test flight, capturing a video of the successful flight. The target range is 20 feet, but the longer the better. So for the requirement analysis, the launching mechanism is that the glider must be hand-thrown for the flight, no active remote or automatic control of the vehicle, and no built-in propulsion systems. So for the size constraints, the glider must fit within a square box of dimensions 16 inches by 16 inches from the top view. As for the structural integrity, the vehicle must remain intact throughout the flight. No shedding of parts is allowed for the flight to be valid. And for the material guidelines, the primary construction material is balsa wood. So my first alternative generation was my tail, and some importance in regards to performance is that the horizontal stabilizer stabilizes the aircraft by counteracting changes in pitch, contributing to a balanced and controlled flight. As for the vertical stabilizer, it prevented unwanted side-to-side oscillations and stabilized the aircraft around its vertical axis. This stability is crucial for maintaining a straight and coordinated flight, especially during changes in direction or wind conditions. So my two main alternatives were between a T-tail and a conventional tail. And a T-tail, some pros are that it's easy to build since there are only two parts and it can be altered to fit any design. And it's efficient to reduce drag, weight, and can be placed above the fuselage. However, a con is that the horizontal stabilizer is very fragile due to structure and material, and it ended up breaking multiple times during testing phases. As for the conventional tail, some pros are that the components of a conventional tail are straightforward to cut and assemble, which is advantageous during building stages, and it provides glider with stability when gliding. It can be easily moved anywhere, allowing for easy manipulation of the center of gravity. However, a con is that the aerodynamic benefit is not up to par when compared to most other tail designs, just because it doesn't provide as many types of benefits. My second alternative generation was a wing. So the pros and cons of each wing iteration are shown below. My two main ones were between the dihedral wing and a straight or no angle wing. So some pros of the dihedral wings were that it provided inherent stability and roll, helping the aircraft resist rolling and maintaining a more level flight altitude. The dihedral effect enhances lateral stability, making the aircraft more resistant to unintended rolling motions caused by gusts or turbulence. Dihedral wings also contribute to a self-correcting tendency. If the aircraft rolls to one side, the dihedral angle helps it return to a more stable level position. However, some cons of that dihedral wing were that it was harder to manufacture due to wings being separated, and they must be positioned at an angle. Wings are bent, making the wings much more prone to breaking if it lands wrongly. However, this could possibly be overcome if reinforced strong enough. So for the straight no angle wing, it was super easy to manufacture since balsa wood just needs to be fastened on top of a fuselage. It also gives a slightly greater lift output when compared to a dihedral wing. However, some cons are that the straight wing does not provide any benefits to stability of glide performance, and aircraft with straight wings may have reduced lateral stability compared to designs with dihedral wings. So for my third alternative generation, I did the assembly adhesive, and it was between the super glue, hot glue, and tape. So for the super glue, it bonded quickly, allowing for rapid assembly of balsa wood components. However, main con was that the bond formed by super glue can be relatively brittle, which may not be ideal for components that experience significant stress or impact. As for the hot glue, it provided a brief window for repositioning parts, which was crucial during the testing phase because it allowed me to move parts around while they were drying. However, a main con is that it can add bulk and weight to the structure. As for the tape, it was easy to apply and requires no special tools or equipment. However, it may not offer the same long-term durability as other adhesive options. In the end, I ended up using a mixture of all three adhesives since they all each had their own pros and cons. For sizing, I wanted to start with wingspan, which is the largest possible, so I decided to start with the 15-inch wingspan. And then I just worked off that and made it shorter and whatnot. In order to achieve center of mass near wings, the fuselage was made to be around half the length of the wingspan. The stabilizers were sized in at approximately 1/4 of the size of the wings, and in order to achieve a high aspect ratio, the root chord was approximately 1.6 inches, while the tip chord was 1 inch. So for the initial concept, my sketch is shown here, and the main design features were that the wings were designed in a dihedral design. The T-tail type was for horizontal and vertical stabilizers. There's a tapered wing planform, and the front of the glider is chamfered to increase aerodynamics. So during the testing, my initial concept was a cardboard prototype. The prototype was made out of cardboard tape and hot sauce packets for weight. So continuing on with my design iterations, when evaluating stability, Play-Doh was added to the front tip of the glider. After playing around with the weight, eventually enough was added so that the center of mass was just at where the quarter cord met the fuselage. And some other iterations were that the material was switched from cardboard to balsa wood to provide a more sturdy glider. So for my prototype performance and improvements, the flight results of the test flights, glider on average went consistently 20 feet. However, the T-tail was way too fragile and kept breaking multiple times. The wings broke as well, but not as frequently as the tail. So some improvements for my final design was that I would create a longer fuselage, get rid of the T-tail design, and reinforce the wings and all their components with duct tape. And here's a video of the best flight for final design. So for my final design, I settled on a 15-inch wingspan with tapered rectangle wind platforms. The wings were super glued to the fuselage at a 5-degree angle, and then duct tape was used to reinforce the wings to the body. The balsa wood fuselage was increased to 11 inches with 4 grams of Play-Doh at the nose, which covered the duct tape so it doesn't fall during the flights. This made the center of gravity maintain at a 1/4 chord. So my lift coefficient calculations are shown below, and it provides formulas and all the variables that are necessary for the calculations, along with a table that track my distance, time, and velocity from practice throws. And then here are the drag coefficient calculations, which is built upon the lift coefficient calculations. And once again, the variable and the formulas are shown here. So here's a video of my final performance at the Burger Bowl Park. So revisiting the initial requirements, fabrication and launch requirements were that the glider was less than the 16 by 16 dimensions given at the start, the glider was hand thrown, the glider remained intact, and the glider utilized balsa wood as the main component. As for performance, the glider met the requirement of going 20 feet, and the glider flew relatively straight due to utilizing components to create aerodynamically stable glides. Lastly, for my summary and concluding thoughts, for the essence of the project, it was an amazing experience to build a glider which integrated key components of aerodynamics that we learned throughout the semester. It was also cool making iterations of designs and applying an engineering mindset to this very open-ended problem. It was also cool getting to spend more time in the AMS by myself, and I got to meet new machinery as well as new people. This even opened my mind to the prospect that I would like to be a mentor there soon. Some areas for improvement, however, was that I could have made the fuselage more sturdy, I could have tried to make the wings curve upward, and I could have slightly decreased the wingspan of the horizontal stabilizer. And here are my references. Thank you so much for watching.